Hello, in this problem, a homeowner plans to pump water from a stream in their backyard to water their lawn. Again, we're assuming that he or she has water rights to do this, at least in Texas. You need irrigation rights to do this. A schematic of the pipe system is shown in the figure, and we'll go over all those questions, or the information, but there's four main questions. Total minor or major losses, and then the power shaft, head required, and for the pump under different assumptions. I'm going to do this problem by parts. You need to be very organized for this type of problem, and for the exam I'm not going to give this as complex a problem, but something like this where you have several couplings or different connectors that you need to take into consideration for the minor losses and of course the major losses. Okay? The first question is, what is the total minor head loss of the system? And this is the equation for minor head losses. First of all, don't be deceived by the word minor and assume that the minor losses are small, because they can be larger than the major losses. So it's just a term we use to define this type of loss. Okay, so let's go one by one here on each one of the components that we have here. We have the entrance, so let's call this 1. Okay, and the KL for this one is 0.8. Then we have this, we'll call this number 2, and the KL for this is 0.1. Then we have the hose, pump to hose coupling, and the KL for this one is 0.2. Then we have, and let's call this 3. And then for number 4, we have the hose-to-hose coupling, and the KL equals 0.5. And then finally we have the sprinkler, and has a KL of 100. The first thing you have to notice is that this coefficients are very small, but the sprinkler coefficient is very, very big. It makes sense because you're releasing all that energy into the air, so all that energy is lost. So we're going to use this expression, but as you can see, the velocity is a variable. So for 1 and 2, we have velocity 1, let's call it. But then for this others, for 3, 4, and specifically 3 and 4, we have V2 is a different velocity. So let's get those velocities first. Here we have 2 meters of 2.570 meters diameter of tubing. So the velocity here is Q divided by A, and the Q is given in the problem as 2.5 times 10 to the minus 4 meter cubic, or cubic meters per second. And then we have the area, 0.25 meters squared over 4. So V1 is 0.51 meters per second. So for this one, the velocity is going to be again Q over A, and we have the same Q, the continuity expression, and then the diameter changes here. So the velocity here for this part is 1.88 meters per second. So the kind of checks you can do is, here the diameter is larger than here, so you expect the velocity here to be smaller than there. So if you did this calculation and obtain a lower or smaller velocity, then you know that you've done something wrong. Okay, so now let's calculate the losses for each pipe. So let's mention for the components for P1, and remember these are the minor losses. So the velocity is 0.51, and we put it all in the basic units, so we don't have to worry. And then here we have 0.1 or 0.8. Let me put it in the same order, plus 0.1. So the 0.8 is the KL1, and this is the KL2. And these are, of course, very small, 2 to 4 meters. Okay. So let's take a look at P2 and P3. So HL equals, now I have 1.88 squared to 9.81, and then we have 0.2 plus 0.5, and then here what we have is, this is 3 and 4, and this is 0.13. Now for the sprinkler, we have on this side of the sprinkler, and we can use the same, but then we have this times 100, and this is 18 point 14. Check the numbers, because I did this real quick, and I want to make sure that I don't give you something that's not correct. Okay, so this would be 0.1, 0.2, 0.5, 0.13. Okay, so this is the 18.01. We have meters. Now, let's do something for fun. One of the things that here it says is this part here, the pressure drop across the sprinkler. And so what we see is, if it's the pressure drop across the sprinkler is, it says it's 210 kilopascals. And this comes from, remember, gamma times H is pressure, so what I'm doing is finding H by having pressure over gamma. Then this is 21.4 meters. So this is a quasi-real problem. I mean, and basically I find problems and make some changes, but in theory, this loss should be equal to that number, but it's not, because of course I made that up. So that means that this KL should have been a little larger. Okay, so moving on, we still have not calculated the total minors head losses, so you have to add everything. 0.024 plus 0.13 plus 18.01. So it's 18.2 meters. So this is the answer. Okay. So let's do the second part. And in the second part, what we are calculating is the major head loss. And for the major head loss, what we have to do is look at these two things, which are the length and the type. Now, the friction factor for the hose, it tells you that it's 0.01. It doesn't give you a friction factor for the run tubing, and really the reason they didn't give it to you is because the losses there are so small. They didn't even consider them. But let's say that you want to do it by the book and consider those losses. You could go Google the drum tubing. Of course, Googling is not something that you'll have the luxury in the exam, but you can check that. And, if you Google the, 0.01 can be used as well. And you'll see what I mean in a moment. So remember that the velocity here is 0.51 meters per second, and the velocity here was 1.88 meters per second. So we calculate the major loss for here, and the friction factor is given, so we have 0.01 and then 2 meters, 0.51 squared, the diameter 0.025 to 9.81, and this is 0.01 meters, so it's very small. Now the head loss for here, you have 0.01, 30.5, because it's 15.225. The velocity is 1.88, 0.013, 2 times 9.81, and this is equal to 422 meters. So see how the minor losses are larger than the major losses, and that happens probably, you see, whenever you have to connect a lot of different hoses at home, you don't get the same flow rate or even pressure. So the total major head losses are 4.22 plus 0.01, and again this part here is very minimal meters. Okay, the next part requires a few assumptions, and it should be a kind of a straightforward, and you can make it as simple or as complicated, but then again, for this class it has to be simple. So basically the information you need is provided. It tells you the sprinkler, the velocity heat at the sprinkler head, and then the head loss. So what is the shaft head required to operate the system at the design flow rate? So if you assume that these are the head losses and that this sprinkler exit, remember most of the minor losses are due to the sprinkler. So if we only consider those losses because the other were not significant, what we have here is that you have between these two losses you have 20 meters. But then you also have to overcome, remember you're going from a low point to a high point, okay? And what you have here is 4 meters. So we have the equation for the power here, CHQ or gamma HQ. Okay, so we have 9810 H, then we have 20 plus 4, and the Q, which is given 0.5 times 10 to the minus 4 cubic meters per second. So let me double check this calculation. Yeah, times 24 times. So we have 58.86 watts. Okay. For this next question then, if we assume, only for this question, that the shaft head required, well, let me go back to this one. So if you were doing it by the book, you would have to incorporate the minor losses from the different components, but the difference will not be significant from this. Okay, and that's all I wanted to say. Then going to the next problem, if you were going to assume that the shaft head required to operate the system at the design flow rate was 100 meters, what is the power in watts? Okay, so same equation we'll use, but now it's 100 meters, so I have here, I'm not going to put the units because I'm using the basic units. Well, let me put it. Meters per second, and then I have 100 meters. So this is 245.3 watts. That is the power that needs to be into the water, to the water, not to the pump, because the pump is 65% efficient. Then this 245.3, you need to supply more. So you divide by 0.65, and then you have 377.3 watts. So that's the answer. I hope this helps. Thank you.